hypothesize a solution of the form U of r, theta, and z is capital R of small r, theta of theta, z of z. We differentiate u to obtain the partial derivatives ur, urr, u theta, theta, and uzz, then plug in into our differential equation. Divide through by u to separate the variables. This is to say u sub r is r prime, theta, and z. urr is r double prime, theta, z. U theta is r theta prime, z. U theta theta is r theta double prime, z. Uz is r theta z prime. Uzz is r theta z double prime. So urr, we have r double prime theta z plus 1 over r prime theta z plus 1 over r squared r theta double prime z plus r theta z double prime equals 0. We divide through by r theta z. So we'll have r double prime theta z divide by r theta z plus 1 over r prime theta z divide by r theta z plus 1 over r squared r theta double prime z divide by r theta z plus r theta z double prime divide by r theta and z. In the first term, theta and z will cancel out. This cancels out. In the second term, we have theta and z again. Oops, we lost that. R double prime over r plus 1 over small r prime over capital R plus theta double prime plus 1 over r squared theta double prime divided by theta plus z double prime divided by z equals 0. We're now good to separate the variables. Z double prime divided by z equals minus r double prime over r plus 1 over r prime over r plus 1 over r squared theta double prime divided by theta. The left hand side is a function of z alone. We have the right hand side is a function of r and theta. For equality to hold, we equate both of them to the same constant. For this particular case, the general solution of Laplace equation in cylindrical coordinates will investigate the case where the constant is positive. So we set this equal to a positive constant, say k squared. That means we'll have z double prime divided by z equals k squared. The other equation is minus r double prime over r plus 1 over r prime over r plus 1 over r squared theta double prime over theta. This is also equal to k squared. And label this equation 1 and the second one equation 2. Let's solve equation 1. Z double prime over z equals k squared. It's the same thing as z double prime equals k z squared, or z double prime minus k z squared equals 0. Z double prime equals k squared z, not the other way around. This is equal to k squared z. Z double prime minus k squared z equals 0 is a second order ordinary differential equation. If you solve for this, what is the general solution?
Z of z is equal to C1 e power. You're using mu. Okay. So k z plus C2 e power negative kz.
You can go ahead and obtain the auxiliary equation first before solving. But we've done this before, so for those who are not able to understand how this comes about, you can consult Calvin, or we've done this before. You start by writing down the characteristic equation, then obtain the roots, then proceed to give a solution. Our equation 2 is minus r double prime over r plus 1 over r prime over r plus 1 over r squared theta double prime over theta equals k squared. We cannot solve this equation as it looks because we need to separate r and theta. So for us to be able to separate r and theta, we'll have to get rid of the r squared, or the 1 over r squared term appearing before theta double prime over theta. To do so, we multiply through by small r squared. If you do this, then you have minus r double prime over r plus 1 over r times r squared gives us r times r prime over r plus theta double prime over theta equals k squared r squared. or minus r double prime over r plus r prime over r plus theta double prime over theta minus k squared r squared equals 0. You can distribute the negative sign. Minus r double prime over r minus r prime over r minus theta double prime over theta minus k squared r squared equals 0, which is equivalent to
Excuse.
go on.
In multiplying by r squared, I think the first term should be having
Sorry?
the first term.
Yes?
We have multiplied by r squared.
Yeah, there's an r squared missing. Thanks for that observation. Let me just scroll up. So if we multiply through by r squared, we have an r squared here. R squared times r double prime over r. There should be an r squared here. Minus r squared, r double prime over r. This is equivalent to r squared, r double prime over r plus r prime over r plus theta double prime over theta plus k squared r squared equals 0. We wish to separate the function of r from the function of theta. So we take theta the other side. We have r squared, r double prime over r plus r prime over r plus k squared r squared equals minus theta double prime divided by theta. Again, in this case, the left-hand side is a function of r alone. The right-hand side is a function of theta alone. This holds true when both are equal to some constant. Say, again, we're investigating the constant positive, so p squared. Let's set the two equations equal to the constant p squared. The first equation is r squared, r double prime over r plus r prime over r plus r squared k squared equals to the constant p squared. The second equation is minus theta double prime over theta equals to p squared. So let's start by solving equation 2. For this case, we have two equations. Let's start by solving the second one. Let's solve this. It's pretty straightforward. Minus theta double prime over theta equals p squared. It's the same thing as minus theta double prime equals p squared theta. If we put everything on the same side, then we have minus theta double prime minus p squared theta equals 0, or theta double prime plus p squared theta equals 0. If you solve this differential equation, clearly you'll get complex roots. So what is theta in this case? Let me just do this one final time. Let me write down the auxiliary equation. So assume theta is e to the mu theta. Theta prime is mu e to the mu theta. Theta double prime is mu squared e to the mu theta. Plug in theta together with its second derivative to the differential equation. You have mu squared e to the mu theta plus p squared e to the mu theta equals 0. Factor out what is common. In this case, e to the mu theta is common, so into mu squared plus p squared equals 0. E to the mu theta cannot be equal to 0. Therefore, mu squared plus p squared must be equal to 0. If this is the case, mu squared equals minus p squared. Mu will be plus or minus root of minus p squared, which is plus or minus ip. If the roots are complex in nature, then you have two solutions. One is cosine is e to the alpha times, in this case, theta times cosine of beta. In this case, our beta is p. The second solution will be e to the alpha times theta plus e to the alpha theta times sine p theta. But our alpha is 0 in this case. So this implies our theta will be some two constants. Did we use C1, C2? Maybe we can use C3, cos p theta plus C4 sine p theta. So the equation involving r is r squared r double prime over r plus r prime over r plus r squared k squared equals p squared. If we put everything on the same side, then set it equal to 0, we have r squared r double prime over r plus r prime over r plus r squared k squared minus p squared equals 0. Let's get rid of the capital R in the denominator, so we multiply through by that capital R. I hope I'm not too fast. I'm really trying to slow down. If you multiply through by R, it will disappear from the first term as well as the second term. But the third and fourth term will have the R, so we have r squared k squared capital R minus p squared capital R equals 0 times R is 0. Let's factor out the R in the last two terms. We have r squared r double prime plus r prime plus r squared k squared minus p squared times R equals 0. So this looks like the Bessel's differential equation, but it's not quite. We have to do some manipulation. The Bessel's differential equation takes the form. Did you guys cover Bessel's differential equation in 3.2? Mr. Differential alifunza hii?
Yes, Belfast, yes.
How does it look like? What's the form of a general second order Bessel's differential equation? Calvin? Anyone? Joseph? ama niwakumbushe?
Yes.
General second order Bessel's is x squared y double prime plus x y prime plus x squared minus p squared times y equals 0. Clearly you can see r squared r double prime. R squared compares with x squared, r prime compares with xy prime. R squared k squared minus p squared compares with x squared minus p squared, then r compares with y. So for it to become Bessel's, we need this term to be some single index squared, not a product of two indices. Just unmute and speak up kindly. I don't want to stop sharing for me to go read this, what you've typed. Who had a concern?
It was just a new student who was just joining, not a
Okay.
question.
Oh, okay. So after separating the variables, we are ending up with the equation involving r is r squared r double prime plus r prime plus r squared times k squared minus p squared times r equals 0. So we need to transform it to become Bessel's. We want this term to be some single index squared. So we use the transformation let x be rk, so that if you square x, it's the same thing as having r squared k squared. So once you set your x equals to rk, you want to transform your differential equation from one involving r to one involving, from one having derivatives with respect to small r to one having derivatives with respect to x. To do that, maybe we can first rewrite our r double prime as partial squared r partial r plus r prime is partial r capital R partial small r plus r squared k squared minus p squared equals 0. So once we let our x equals rk, we want to write our partial r with respect to small r in terms of the partial derivative with respect to x. We know that chain rule permits us to write this as partial r, partial x, partial small r, right? Are we at par?
Yes.
So if partial r, partial capital R, partial small r is equal to this, we can obtain partial x, partial r from x equals rk implies partial x, partial r is the partial derivative with respect to r of the quantity x, but x is equal to rk. If we differentiate rk partially with respect to r holding k constant, what do we get? What is partial r or of rk?
K.
We get K. So this tells us our partial r, partial small r is equal to partial r, partial x times K. You can rearrange so that you start with K. This is equal to K times partial r, partial x. So we can substitute partial r, partial small r with K partial r, partial x. Next, we have to transform partial squared capital R, partial small r squared. But this is the first partial derivative with respect to r. Is the partial derivative with respect to r of the first partial derivative of capital R with respect to r. So this is partial r of the first partial derivative, but we've found this to be equal to K partial r, partial x. So we want partial r of K times partial r, partial x. Clearly K is a constant. Factor out the constant, then take partial r of partial r, partial x. If we were to expand partial r times partial r, partial x, then we will get partial squared capital R, partial x. But when evaluating partial derivatives, at least for the second order, for up to order 2, the order doesn't matter. If you have, don't write this, if I have partial squared y, partial x, partial y, and I say this is partial squared y, partial x, means the same thing, right? Order doesn't matter. So if I rewrite these as partial squared r, partial x, partial r, then means the same thing. So this is equal to K times partial squared r, partial x, partial small r. We can split this again and say this is partial x of partial capital R, partial small r. Still the same thing, right? Are we still together?
Yes.
Thing is, we do not want a partial r in the denominator. So we have to proceed by following all these steps. This is K partial x of, now we use chain rule. How can we write partial r, partial x, partial r in terms of x?
Partial r, partial x times partial x over partial r.
But we know partial x, partial r, right?
Yes.
This is K partial x of partial r, partial x times, what is partial x, partial r?
K.
It's K. Again, let's factor out the K. If we combine it with the other K, we have K squared partial x of partial r, partial x. We've successfully gotten rid of the partial little r. So this is K squared partial x of partial r, partial x, partial squared capital R, partial x squared. We're now good to go. Using partial r, partial little r equals K partial r, partial x, and we hadn't labeled the equation, so anyway, so we'll just say using this, and partial squared capital R, partial small r squared equals K squared partial squared r, partial x squared. We have the following. we had an r squared partial squared r partial x squared. So we will r squared times the second partial derivative is k squared partial squared capital R partial x squared plus r partial r. So k times partial capital R partial x plus, here we had r squared k squared minus p squared equals 0.
Excuse me, could you please scroll up?
Tell me where to stop.
There. Yeah, you can now scroll down. Thank you.
We started this transformation by setting rk equals to x. So that means if rk is equal to x, then r squared k squared should be equal to x squared, right? So in place of r squared k squared, we use x squared. In place of rk, we substitute with x.
Excuse.
Yeah, sorry?
Where you've written r squared k squared minus p squared, there's supposed to be a capital R in that part, I think.
Outside.
Yeah.
Times r equals 0. So using this, r squared k squared, we substitute with x squared partial squared r partial x squared plus rk, we substitute with x, so partial r partial x plus r squared k squared, substitute with x squared minus p squared times r equals 0. It's now Bessel's, isn't it? X squared r double prime plus x r prime plus x squared minus p squared times r equals 0. You can label this as star, then proceed to say star is a Bessel's differential equation. The initials dE stand for differential equation, whose general solution is given by I hope I'm not too fast. Can I proceed?
Yes.
So Bessel's dE, whose general solution is given by case 1, when p is not an integer, we had used the constants up to C4. So C5 jp of x plus C6 j minus p of x x equals rk. So this implies C5 jp of rk plus C6 j minus p of rk.
Excuse me, could you scroll back a bit?
So when you solve the Bessel's differential equation, you end up with Bessel functions up to what point? Is this okay?
Yeah, that's okay.
So when p is not an integer, you will have some constant times jp of x plus another constant times j minus p of x. But in our differential equation, x is equal to rk. So it implies your solution will be C5 jp of rk plus C6 j minus p of rk, where jp of rk is a Bessel function. It's a Bessel function of the first kind of order p. J minus p of rk is a Bessel function of the first kind of order minus p. That is case 1. Case 2, when p is an integer or in general. Now let's give an expression for jp first. Sorry. Anyways, we can just write, I'll give it afterwards, no problem, because my screen decided to misbehave. When p is an integer or in general, then the solution will be given by, we've used up to C6. R will be given by, I think I forgot to indicate this. I forgot to indicate that this is R, the solution capital R. We're trying to solve for capital R. R will be equal to C5 jp of rk plus C6 j minus p of rk when p is not an integer. When p is an integer or in general, solution will be given by R is equal to C7 jp of rk plus C8 yp of rk, where we've defined jp, it's the Bessel function of first kind of order p. We need to define yp. Yp is the Bessel function of second kind of order p. We can give what jp stands for. Jp of rk,
YP. Is it
yp of rk, yp of rk. Where yp is the Bessel function of the second kind of order p. Jp of rk is given as, were you taken through series solution of the Bessel differential equation? Did you come across something that looks like this? Summation from k is 0 to infinity minus 1 to power k divided by k factorial, gamma of k plus p plus 1 times, we are looking at JP of RK, so we have RK over 2 raised to 2K plus P. Did you come across something that looks like this in 3.2?
Yes.
So you know how to derive this, right? You know how to arrive at this, sindio? J minus P, Mr. DiFrangio taught this. He's thorough. K is 0 to infinity, minus 1 to the K divided by K factorial, gamma of K minus P plus 1, RK over 2 raised to 2K minus P. Yn of RK is some constant A times natural log of RK plus B times JP of X plus some function capital F of RK, where this function involves positive and negative powers of RK. Which method did you use to solve the Bessel's differential equation? Maybe I need to know whether I need to give you a recap or just proceed. Positive and negative, let me just write in full. Joseph? Which method did you use? Anyways, let's give the general solution. We need to give the general solution of Laplace equation in cylindrical coordinates. The general solution of Laplace equation in cylindrical coordinates is u the function r times r theta times theta z times z. So for r, we'll pick the solution corresponding to the general case, so where p is an integer or in general. So we'll pick the one having Bessel function of the second kind of order p. Let's give the product. What was our z again? C1 e to the kz plus C2 e2 minus kz, if I'm not wrong, times, what was our theta?
C3 sin P theta on cos, okay, plus C4 sin P theta.
We're multiplying these, we don't lose it, times our r, the solution corresponding to the general case, what do we have?
7 JP RK over 2.
Just a sec. why not J? Calvin, which method did you use to solve the Bessel differential equation?
Our series.
Our series. This is not J. Are you guys familiar, or you guys need a quick refreshing? I don't know. Plus C8YP of RK. Can I trust that you guys know how to arrive at the Bessel functions and proceed to spherical? Or do we go through the solution?
We go through.
Okay. Can be tedious. Okay. So we say this is a recap. The gamma function. Did you go through the gamma function? Okay, let me just assume the lecturer did not teach. This is going to be a marathon. Because usually when I teach series solution, the Bessel's differential equation alone takes like slightly over 1 hour before we arrive at the JP. But anyway, let's see. Consider the Bessel differential equation. X squared y double prime plus x y prime plus x squared minus p squared y equals 0. This is where p is a member of the reals. The solutions, the solution to this dE, the solutions are known as Bessel functions. How do they arise? Vibrations of an elastic membrane, solution of the 3D wave equation in spherical coordinates, we also have 2D water flow in rectangular domain, we've also seen it arises from solution of the Laplace equation, the 3D Laplace equation in cylindrical coordinates and so on, but this is inconsequential. So to solve, we hypothesize a solution of the form y of x is equal to x to the k, summation from k is 0 to infinity, s sub k x to the s, which can be written as, if we combine the x's, summation from k is 0 to infinity a sub k x to the k plus s. And it's assumed that at least one of the coefficients should be non-zero, and in this case, a naught should be different from 0. Maybe I need to specify that this method is the series solution method of Frobenius. So starting from our y, we are using y equals summation from k is 0 to infinity a sub k x to the k plus s. When solving differential equations, whenever you assume that a given function is a solution, then it has to satisfy the differential equation. So what does that mean? It means when you plug in that particular solution together with its derivatives, it should satisfy the dE. In our dE, we need the two derivatives y prime as well as y double prime. To obtain them, we differentiate our function. So y prime of x will be the derivative of summation from k is 0 to infinity a sub k x to the k plus s. Anything that doesn't have an x is treated as a constant, including the summation symbol. So we write the summation symbol as it is, summation k is 0 to infinity a sub k. We also treat it as a constant. Then we differentiate x to the k plus s. We use the general power rule. It says we pre-multiply by the power. The power in this case is k plus s. Then we multiply by our original function, but we decrease the power by 1. So k plus s minus 1. Y double prime is the derivative of y prime. Again, summation k is 0 to infinity. Write it as it appears, a sub k. We'll have a k plus s. We pre-multiply by the new power. So a sub k, the summation symbol together with k plus s are treated constant. Then we want to differentiate x raised to power k plus s minus 1. So to do that, we pre-multiply by the power of x, which in this case is k plus s minus 1 times our x raised to the power decreased by 1. We'll have k plus s minus 1 minus 1, k plus s minus 2. I hope we are together. So once you have your derivatives together with the function, you insert into the differential equation. So maybe I can communicate that inserting y prime and y double prime into the differential equation. What do we have? The dE says x squared y double prime. So x squared times our y double prime is summation from k is 0 to infinity a sub k, k plus s minus 1, x to the k plus s minus 2, plus x y prime. Y prime is summation from k is 0 to infinity s sub k times k plus s, x to the k plus s minus 1, plus x squared minus p squared times y. Y is summation from k is 0 to infinity s sub k x to the k plus s. We need to set this equal to 0. So if y equals summation from k is 0 to infinity s sub k x to the k plus s is a solution to this differential equation, then it has to satisfy this. In other words, we need to check the conditions on what is the index s. We also need to come up with the recurrence relation and then try to determine a few terms, then generalize. So we can simplify this from the first term, x squared summation. If you combine the x's together, what do you have? From the first term, what do we have? Combine x squared. Go on.
AK, k plus s, k plus s minus 1, and then x, k plus s.
K plus s minus 1, x to the k plus s. For the second term, combine the
AK,
x's together. AK, k plus s.
s, and then k plus x power k plus s.
So for the last term, we need to distribute the x squared minus p squared. Distribute, combine the x's together, term by term. So starting with the x squared plus summation from k is 0 to infinity, ak x to the Brian? You're combining x squared and x to the k plus s. You're just summing the powers. What do we have here?
K plus s plus 2.
K plus s plus 2. We have a minus p squared summation k is 0 to infinity, ak x to the k plus s. So with the series solution method of Frobenius, we need that everything should be raised to k plus s. The power should be k plus s for all the terms. For the first term, we have x to the k plus s. For the second term, x to the k plus s. The third term, it's not x to the k plus s. For the fourth term, it's x to the k plus s. So that means we have to do some algebraic manipulation to the third term. We need the power to be x to the k plus s. So for the third term, letting m be equals to k plus 2 in the third term. For the third term, we have an x to the k plus s plus 2, right? But we want these to be x to the k plus s. So if we let this k plus 2 be equal to m, then it will mimic k plus s in some way, right? I hope you understand. So if you let m equals to k plus 2, or the k plus 2 equals m in the second term, then it means our k is equal to m minus 2. Remember you are summing your series, you are summing over the values of k, but you are doing some manipulations and then you are introducing a different index m. That means you're going to sum over m, because in place of k plus 2, you're going to substitute with m. Your k was running from 0 to infinity. You need to investigate whether m will have the same property or not. M is k plus 2. K is running from 0 to infinity. When k is 0, m will be 0 plus 2. This is equal to 2. When k is infinity, m will be infinity plus 2. Big number plus some small number or plus anything is equal to the same big number. This implies our 0 is our m is between, no, sorry, not 0, 2 is less or equal to m is less or equal to infinity. So we rewrite the third term. We are going to sum over the values of m, and m is running from 2 to infinity. We had an s sub k, but what is our k? Our k is m minus 2. X to the k plus s plus 2. K is m minus 2 plus s plus 2. What do you have? M plus s, right? You know, if you don't respond, I won't know whether I'm talking to myself or something, because with online, anything is really possible. I could be logged out of the meeting unknowingly. So I'll be there talking to myself, thinking you guys are, following. Are we together?
Yes.
So you have the third term reducing to summation m is 2 to Is this all we have, or are we missing something? We had an AK times what times what? I think there's something missing. I'm not sure. AM minus 2 times. Is this okay?
Yes, it's okay.
Yes, it is.
So summation from m is 2 to infinity am minus 2x to the ms. We argue that this is the same thing as when you sum. If we use L instead of M, will we lose anything? Are we changing our results? It will be the same thing, right?
Yes.
So you see, instead of M slash L, use K, since all the indices M, L, K are just but dummy indices. So this implies our third term becomes summation from k equals 2 to infinity ak minus 2 x to the k plus s. And we have the power being k plus s as desired. So now we can rewrite the whole thing. What did we have? What are the first two terms?
Summation of k from 0 to infinity of ak k plus s minus 1 x power k plus s plus
The second term plus
summation of k from 0 to infinity ak k plus s and then plus the third term we have summation of k from 2 to infinity ak minus 2 x k plus power k plus 2 minus p squared
minus p squared
summation of k from 0 to infinity ak k
x to the k
x
plus
power
s.
yes.
Okay, I need you guys to help me out. This wasn't part of this course. So it's not like I've written these things down. I rely on you to help me check the previous step. Like I know how to solve, but I can't, memorize that in our previous step, this is what we had. So I will need your help pretty much. So once you're done with setting the powers equal, like once you have all the powers, all the x's raised to the same power, the next thing is you want all your indices to run from the same value. For the first term, k is running from 0 to infinity. For the second term, the same thing, k is running from 0 to infinity. For the third term, k is running from 2 to infinity. For the fourth term, it's 0 to infinity. So the next step is you reindexing. With reindexing, you want to make sure that all the indices run from the highest all the way to infinity. So between 0 and 2, which one is higher or which one is bigger than the other one? Of course, 2 is bigger than 0. So you want everything to run from 2 to infinity. But that is not the case for the first, the second, and the fourth terms. So what you do, you take values corresponding to, but don't write this. Let me just try to illustrate something. If I'm summing from n is 0 to infinity, and then let's say I have an x to power n, this will be the same thing as I have my x raised to the first power when n is 0, plus x raised to the first power when n is 1, plus when n is 2. So if I stop here, I've taken the value corresponding to n is 0 plus value corresponding to n is 1. That means I'll be remaining with the summation over the values from n equals to all the way to infinity, x power n, right? You'll get the same thing, right? So for you
Yes.
to reindex, you want to take separate values corresponding to k equals 0 and k equals 1 for the first, second, and fourth terms. Once you do that, then you will be able to sum everything starting from 2 to infinity. So that's the next thing we're going to do, reindexing. So taking values for k equals 0, 1 separately for the first, second, and fourth terms, and then summing everything from 2 to infinity. We have the following: everything from 2 to infinity. We have the following. So I need your help. I need you to take k equals 0 for the first term. Tell me what you get. Take k equals 1. Tell me what to write. Go to the second term as well. Take the value for k is 0, k is 1. Go to the fourth term. Give me the value for k is 0, k is 1. Then we sum everything from k is 2 to infinity. So starting with the first term, when k is 0, what do you have? If this was physical, I would have just confirmed from the other side of the board and written down. But now I need you guys to help me. When k is 0, what do you have for the first term? From the first term?
A0.
Give me a minute. I have to connect my charger. Okay, now it's A naught. It's A sub K. So when A is 0, A naught,
S
S,
times S minus 1.
is it minus or plus? K plus S minus 1. S minus 1,
X power S.
X power S plus, we are summing. Is this the value corresponding to K equals 0?
Yes.
For K equals 1,
A sub 1. S plus 1 times S and X power S plus 1.
S plus 1 plus, we are done with the first term. We take K is 0, K is 1 for the second term.
For the second
Maybe
term,
we can write the sum from K is 2 to infinity, AK, K plus S minus 1, X to the K plus S, right? Yeah, we can just do this, because once we obtain values for 0 and 1, we can sum the remaining series from 2 to infinity. So we go to the second term, take K is 0,
A naught times S times X power S.
it's just A naught S times X to the S.
Yes.
Uh-huh.
Plus A1 S plus 1 X power S plus 1.
Plus, what are we summing?
AK times K plus S X power K plus X.
The third term is in the right form. We are summing from K is 2 to infinity. What are we summing?
K minus 2.
X to the K plus S.
Yes.
Plus, no, the fourth term is a minus.
Yes.
Minus P squared
A naught
times A naught.
X
No, we can
power
just distribute the minus. I don't have to do 2 steps here. Remember to remind me. P squared A naught
X power S minus P squared A1 X power S plus 1.
then as
Minus P squared summation from K is equal
2
to
to
0 to
infinity
infinity. AK X K plus S.
Once you have this, you now collect the like terms together. So start with terms raised to power. We have X power S, coefficients of X to the S. We have X to the S plus 1. Then we have coefficients of X to the K plus S. So let's start with coefficients of X to the S. It's actually supposed to be equal to 0. I've not put an equal sign. Let me just scroll up. Plus this is supposed to be equal to 0. On the right side, you are having a 0. On the left side, you are having different powers of x. When can this be true? This can be true when the x vanishes or when all the coefficients of x are set equal to 0 separately. So let's start with coefficients of x power s. Coefficients of x. Coefficients of powers of x. Because for a power series to be equal to 0, it holds true when all the coefficients of the different powers of x are set equal to 0 separately. So let's start with 1. We need the coefficients of x to power s set equal to 0. So for coefficients of x power s, what do we have?
A naught s
A naught s
plus A naught s times s minus 1 minus p squared A naught.
minus p squared a naught.
Yes.
Any other?
No.
We can factor out a naught. It's common, so we have an s plus s into s minus 1 minus p squared times a naught. We need to set this equal to 0. This is s plus s squared minus s. If we expand the second term, this is what we get, right? S plus s squared minus s minus p squared times a naught equals 0. S plus s squared minus s minus p squared, the s cancels out, s minus s. So we have s squared minus p squared times a naught is equal to 0. S squared minus p squared is clearly a difference of two squares. It can be written as s minus p, s plus p. So this times a naught is equal to 0. Maybe I should have mentioned that equating the coefficient of the lowest power of x. The lowest power in this case is x power s, right? Lowest power of x equal to 0, and solving gives us something which we call the initial solution. Yields the initial solution. And we are having the initial solution, or rather the solution that will give us the indices s minus p, s plus p, then times a naught equals 0. But remember how we defined our Bessel's differential equation after assuming a solution of the form summation from k is 0 to infinity a sub k x to the k plus s. We had let our a naught be different from 0. If a naught is different from 0 and this product is equal to 0, then if a naught is not equal to 0, then by all means s minus p times s plus p must be equal to 0. Solving s minus p, s plus p equals 0 yields, we'll have s minus p equals 0, implying s equals p, or s plus p equals 0 implies s equals minus p. So it yields the indices s equals p and s equals minus p and s equals minus p. So as we've solved for the indices, next we proceed to solve the coefficients of x to the s plus 1, because the coefficients of all the powers of x must be set equal to 0 separately. Next, we need to check coefficients of x to the s plus 1. We need to equate this to 0 and then solve. What do we have?
A1 s times s plus 1.
A1, we are just extracting the coefficients, so leave outside the x power s plus 1. A1
S
s
times s plus 1.
times s plus 1. Oh, okay. This is what you meant. I thought you had said x to the s plus 1. Plus
Plus A1 s plus 1
A1 s plus 1
minus p squared A1.
A1 into s plus 1. Is this all? Is this it for this term?
Yes.
Minus
P squared A1.
p squared A1
Yes.
equals 0.
Yes.
So A1 is common again. Factor out A1. Aha, that was too fast. We factor out A1. Then we'll have s into s plus 1 plus s plus 1 minus p squared. Factor out A1. This is equal to 0. If you expand s times s plus 1, my screen is misbehaving. Oops. Ha. Okay, allow me to write here. If you distribute the s in the first part, s times s plus 1 is s squared plus s, right? Plus, what do we have next?
Plus s plus 1 minus p squared.
Times a0 times a1 equals 0.
Yes.
S squared plus s, you have s squared plus 2s plus 1 minus p squared times a1 equals 0. S squared plus 2s plus 1. How can we write s squared plus 2s plus 1? S squared plus 2s plus 1 is s plus 1 squared. Is it?
Yes.
So this implies s plus 1 squared minus p squared times a1 is equal to 0. Again, we have a form that mimics a difference of two squares, right? Where our a, it looks like s squared minus b squared, right?
Yes.
When you have a squared minus b squared, you can write this as a minus b, a plus b. We have an s plus 1 squared minus p squared. That is to say your a is s plus 1, your b is p. So if we use this difference of two squares to rewrite the above, it means we have s plus 1 plus p times s plus 1 minus p times a1 equals 0, isn't it?
Yes.
So we want to solve for this. This is equal to 0. This product is equal to 0. It's for this to be true, then we either need s plus 1 plus p, s plus 1 minus p equals 0, or a1 equals 0. But from the first part, when solving for the coefficients of x power s equals 0, we found that our s is either equal to p or s equals minus p. When s equals p, it implies we'll have p plus 1 plus p, 2p plus 1, p plus 1 minus p times 1. 2p plus 1 times 1 is 2p plus 1. Remember, from the definition of the Bessel differential equation, I specified that p is a real number, so it cannot be equal to 0 by all means. Same thing when s equals minus p. Then s plus p plus 1 will be minus p plus 1. S minus p plus 1 will be minus p plus 1. So you have 1 times minus 2p plus 1. Minus 2p plus 1 is not equal to 0 because p is a real number. So we are having that the bracket containing the indices is not equal to 0, and therefore a1 must be equal to 0. a1 equals 0. So when solving for the coefficients of x to the s plus 1, we are arriving at a1 equals 0. I think we are left with the coefficients of x to the k plus s. We solve the coefficients of x to the k plus s to obtain the recurrence stroke recursion formula. Will give us the recurrence relation or recursion formula, whichever. So if we extract the coefficients of x to the k plus s, what do we have?
Summation from k is equal to 2 to infinity. ak k plus s times k plus s minus 1 plus summation from k is equal to 2 to infinity.
We can decide that the summation is common. We have it factored outside. So just give me the terms.
Okay, ak into k plus s, ak minus 2
Plus ak minus 2
minus p squared ak.
minus p squared ak
Yes.
equals 0.
Yes.
So let's combine together terms with s sub k. So this implies summation from k is 2 to infinity into brackets k plus s, k plus s, k plus s minus 1 plus k plus s minus p squared times ak plus summation from k is 2 to infinity s sub k minus 2 equals 0. Distribute the k plus s in the first bracket. You have k plus s times k plus s minus 1. What is k into k plus s minus 1 plus s into k plus s minus 1 plus k plus s minus p squared? We are having an ak outside plus ak minus 2 equals 0. Again, we are leaving out the summation symbol. K into k plus s, you have k squared plus ks minus k plus s into k plus s, sk plus s squared minus s plus k plus s minus p squared times ak, then plus ak minus 2 equals 0. Are there any terms that are going to cancel out in the first part? What can we group together? What can we add? I think I'm seeing a minus k and a positive k. Minus k, positive k cancels out. Minus s plus s cancels out. Ks plus sk, 2ks. Are we together?
Yes.
K squared plus 2ks plus s squared minus p squared ak plus ak minus 2 equals 0. Again, k squared plus 2ks plus s squared. If I write k squared plus 2ks plus s squared as k plus s squared, is it the same thing?
Yes.
So we have k plus s squared minus p squared times ak plus ak minus 2 equals 0. Again, let's use the property of the difference of two squares to rewrite the first bracket. So what do we have?
K plus S plus P.
K plus S plus P. K plus S minus P times AK plus AK minus 2 equals 0. So this is what will help us determine the recurrence relation, but you're now solving for a higher index in terms of the lower index. If we do that, what will be the formula? You first isolate the lower index as much as you can, then do what you go to do to solve for the higher index in terms of the lower. Between k and k minus 2, k is running from 2 to infinity. Which one is bigger? S sub k or S sub k minus 2k, right? Okay, so what do we do? What do I write? To solve for the higher index S sub k, what is the formula? Come on, guys. It's right on your screens. You're solving for x sub k from that product you see on your screens. First things first, you'll isolate S sub k minus 2. Take it to the other side. You remain with S sub k, but it has some coefficient. So what do you do? What is the formula?
Negative.
Minus AK minus 2 divided by K plus S plus P, K plus S minus P, but K is running from 2 to infinity, so you have to specify that K is greater or equal to 2. This is the recurrence relation. The recurrence relation. But when you solved for the indices, we found two values. One of the index was S equals P, the other one was S equals minus P. So we'll have two solutions. You write down the two solutions. First, you will have solution corresponding to the first index, corresponding to S equals P. Solution corresponding to S is equal to P. Go back to your recurrence relation. It's given by A sub K equals minus AK minus 2 divided by K plus S plus P. K plus, in place of S, substitute with P. So K plus P plus P. K minus S, K plus S minus P. K, oops, the screen. K plus S plus P, but S is equal to P. So you have K plus P minus P. This is minus AK minus 2 divided by K plus P plus P. P plus P is 2P, so K plus 2P. K plus P minus P is just K. So solution corresponding to the index S equals P will be given by A sub K is solved by using the formula A sub K minus 2 divided by K plus 2P times K. If you start with K or start with K plus 2P then times K, it's the same thing. But you have to specify that K is greater or equal to 2. So this is the recurrence relation. For you to be able to arrive at the Bessel functions, using this relation, you try to generate a few terms and see what you get. Once you get a few terms, you can be able to generalize the results. Of course, you will see the pattern. Obtain the first few terms, see the pattern, derive the formula that corresponds to the pattern you're seeing, then go ahead and give your GSL function. So K is greater or equal to 2 means we start with K equals 2. When K is 2, A sub K will be A sub 2 equals minus A sub K minus 2. So we'll have a 2 minus 2 here. What do we have? 2 minus 2 is 0. A naught, right? Divide by, so you have minus A naught divided by K is 2. K plus 2P, 2 plus 2P, which you can rewrite as minus A naught divided by 2 times. You can factor out what is common in the first bracket. What is common in this case?
It's 2.
2 is common. 2 into 1 plus P. So you can proceed to combine the 2 and 2 and say this is 2 raised to power 2 times 1 plus P or P plus 1. It's the same thing. When P is 2, when K is 2, you have A2 is minus A naught over 2 raised to 2 times P plus 1. When K is 3, K equals 3, we'll have A sub 3 equals, what do we have here?
Negative A1.
Minus A1 divided by 3 into 3 plus 2P, right?
Yes.
But when solving for the coefficients of x to the s plus 1, what did we find out to be equal to our A1? What was our A1?
0.
It was 0. So this implies A3 will be 0 divided by anything, it's 0. Similarly, A5 will be given in terms of A3, right?
Yes.
We need to generalize. So similarly, we have A1 equals A3 equals A5 equals A7 and so on will be equal to 0. In other words, this tells us that we need to only concentrate on the even values of K, because the odd values will result to zeros. So we only concentrate on the even values of K. Let's obtain an expression for when K is 4 and K is 6, then see if we can determine the pattern. When K is 4, we have F4 equals minus A2 divided by 4 into 4 plus 2P. But we had obtained the results for A2, right? What is our A2? We just derived it.
Negative A naught.
So our A4 is minus A2. So we have a minus, then our A2 is minus A naught. But A4 is minus A2 divided by 4 into 4 plus 2P. So we write that first, then we write the A2. A2 is minus A naught over 2 squared into 1 plus P, or P plus 1, whichever.
Yes.
Minus A naught will become positive A naught. Oops, aha. That was fast. I need to see the results. Let me just, screen is, so F4 is equal to, F4 is positive A naught divided by 4 is the same thing as, first we have a 4 here, then we factor out what is common from this bracket. 2 is common, we'll have 2 plus P. Then we are multiplying with 2 raised to power 2, then P plus 1. This is positive A naught divided by 4 is the same thing as 2 squared. The 2 squared, you have 2 power 4 times 2 times P plus 2, P plus 1. We can actually start with P plus 1 first. So we have positive A naught divided by 2 power 4 times 2, then times P plus 1 times P plus 2. The next value of K is, we consider K equals 6 because the odd values will give us zeros. So when K equals 6, from the recurrence relation, what do we have? Cheryl? When K is equal to 6?
Negative A. Well,
So we are starting from the left-hand side. What do we have on the left-hand side?
A6.
A sub 6 equals minus
A4.
A4 divided by
6 into
6,
6 plus
6 plus 2P. What do we do? Minus A4 first. We factor out what is common in the bracket, right?
yes.
So what is common in this case?
2, 3 plus P.
3 plus P. But we have an expression for A4, so we can use it here. Our A6 is given in terms of A4, but we have our A4. So we'll have minus, let me just say minus 1 divided by 6 times 2 into P plus 3 times, what is our A4?
A naught over
A naught over
2 power 4 times 2
2 power 4 times 2
times P plus 1
P plus 1 times P plus 2.
Yes.
So this is equal to minus A naught divided by, if we combine 2 power 4, 2 power 1, we get 2 power 5. Combined with this other 2, we get 2 power 6. So if we write this as 2 power 6 times 6, then times, we have P plus 1, P plus 2, P plus 3, right? If we were to write down the first few terms we have, one of the things that's clearly coming out is that this formula will only help us determine the positive or the values for even values of k. So using the three terms, we can deduce a formula for a sub 2k, because this is how to write an even number. When k is 0, you'll get a2. When k is 2, you get a4, and so on. I mean, when k is 2, you get a4. When k is 4, you get a8, and so on. So we can obtain an expression for a sub 2k by just observing the pattern using the first three terms that we've derived. We have a2, we have a4, and a6. Maybe you can tell me the terms, because we need to determine the pattern using these three terms. This was minus a naught divided by 2 power 2 into p plus 1. If I say that this is equal to minus a naught divided by 2 power 2 times 1, means the same thing, right? Calvin. Is Calvin still in the meeting?
Yes, it means the same thing.
Okay. Our F4, what was our F4?
Not
A naught divided by
2 power 4
2 power 4 times 2
yeah
times p plus 1 times p plus 2. So if I say my A2, if I say that this is minus a naught divided by 2 squared times 1 factorial times p plus 1. 1 factorial is 1, right? If I say that this is a naught divided by 2 raised to power 4 times 2 factorial, then times p plus 1 times p plus 2. We still have the same results, isn't it? What is our A6?
not
Is it positive or negative?
negative.
Minus a naught divided by
2 power 6
2 power 6
and
times
6
6 times
p plus 1
p plus 2 p plus 3. If I say that this is minus a naught divided by 2 power 6, how can I write 6 in terms of the factorial?
3 factorial.
3 factorial. So p plus 1, p plus 2, p plus 3. I want you guys to look at the pattern. Try to deduce the pattern. First of all, what is evident is the alternating signs. A2 is negative, A4 is positive, A6 is negative. To take care of the negative or the alternating signs, what do we use? We need to try to give a formula for A sub 2k. Maybe I can say the steps. 1, we are having alternating signs. What do we use to have alternating signs?
Negative 1 power k.
We'll have minus 1 power k. Number 2, what are we having? What is common? we are having some 2 raised to power something. Compare the 2 raised to power 2 in the first part with k. Compare 2 raised to power 4 with k. Then compare 2 raised to power 6 with the appropriate k. What are we having? 2 raised to power
2k.
2 raised to power A6, we have 2 power 6. A4, we are having a 2 power 4. A2, we are having a 2 power 2.
2 power k.
So we have 2 power k. Then the factorial. Look at the factorial function. For A2, we are having 1 factorial. Compare 1 and the value of k, which is 2. For A4, we are having 2 factorial. Compare 2 with the value of k, which is 4. Then for A6, we are having 3 factorial. So how is the factorial defined in this case? Is it k factorial? Is it k minus something? Is it k divided by something? 1
K
factorial,
divide by
compare 1 and 2. What happened? Starting from 2, how can you arrive at 1? Look
K
at
divide
4.
by
Then you're
2.
having, so k divided by 2, right?
2.
K divided by
Yeah.
2 factorial. Then finally, we look at the p, the p series. You have a p plus 1. For the first term, you only have p plus 1. Compare the p plus something, that value plus k again. It's a series. It's running from p plus 1 all the way up to p plus something. But look at k and look at the last value of, the last term of the p series. Then try to determine the formula. So for A2, you just have a p plus 1. Look at 1 and the value of k, which is 2. What happened? Look at the second term. You're starting from p plus 1. You'll multiply all the way up to p plus something in regards to k. So for the second term, k is 4. You're starting at p plus 1. You're ending at p plus 2. Look at 2 and 4. For the third term, you're starting from p plus 1 all the way up to the last one is p plus 3. Look at 3 and then look at the value of k, which is 6 in this case. So what will be the pattern? You'll have a p plus 1, p plus 1, p plus 2, all the way up to, what is the formula for the last term?
P plus k over 2.
P plus k over 2. So now we can write down the formula for A2k using this. Our A sub 2k will be minus 1 raised to power k. To take care of the alternating signs, times all the even values are expressed in terms of A naught divided by 2 raised to the 2k. Then here we had the factorial is k over 2, right? But our k in this case is 2k. So we have a 2k over 2 factorial. Then we have p plus 1, p plus 2, all the way up to p plus k over 2. But our k in this case is 2k. So p plus 2k over 2. That will be the last term. Let's simplify 2k divided by 2.
Excuse me, madam.
Yes.
Can we continue tomorrow?
Now let's finish the recurrence formula first. We'll pick it up from that tomorrow. So this is minus 1. Okay.
Even as we finish,
Yes.
as we finish, can you consider next time? Some students are, some goals for their practice. It is when kuna jobs za jioni, so the blame is more than you think. So
Sorry?
next time tumalize mapema.
We started at 3:10. Or was it 3:12? We have to take 2 hours.
But
Minus
hiyo
1
sasa
power
ni
k.
focus here.
And not 5th years. You guys are not supposed to be complaining that much. So mnafaa ku graduate next year. Supposed to invite me to come with my village people. We will hire school buses, yellow buses with bananas on the sides. Nikuje na maua hizo shanga niwavalishe. 2 to the 2k. 2k divided by 2 is just k, so we have k factorial. P plus 1, p plus 2, all the way up to p plus k. Okay, can stop there. I'm the best thing that happened to you, so I don't have to make you guys start thinking otherwise. We'll pick it up from there tomorrow. Kesho mwamke mapema. Start joining the meeting at 7:45 so that we can start at around 7:50 or thereabout. As we can see, it's quite a lot.
And then finish at what time?
11.